This is a tutorial video on chemistry topic 2, looking at the states of matter. In this video we will look over the difference between particles in solids, liquids and gases. We will have a look at the arrangement, movement and energy of particles as they move between states, and we will have a look at melting point data. Our big question today is looking at the changes that occur when a solid changes to a liquid and then onto a gas, referring to the arrangement, movement and energy of the particles involved. States of matter refers to the three major states. These are solids, liquids and gases. For example, water, which is all around us, can easily exist in all three of these states. We have a solid when it's known as ice, liquid as water, and then finally gas as steam. We can easily move between these states. Going from left to right, we have an increase in the amount of thermal energy and therefore an increase in the kinetic energy of the particles involved. Going from a solid to a liquid is known as melting. Liquid to gas is evaporation. Going the other way, we can condense a gas back to a liquid and then freeze a liquid down to a solid. We can also go straight from a solid to a gas, known as sublimation, and finally from a gas to a solid, known as deposition. At GCSE, you need to be able to both draw and identify diagrams showing the different states. Moving from left to right, we have solids, liquids, and gases. In a solid, all of the particles are arranged neatly into rows. This means that the particles are very, very close together. They still have energy, they are still vibrating around a fixed spot, however they do not move from their positions. As we heat it, the vibrations increase and the forces bonding the whole thing together start to weaken. When this happens, we move into the liquid phase. In the liquid state, the particles can now move over each other. They are able to flow. However, the particles are still touching each other. They have more energy than they did as a solid, but not as much energy as they will do when they become a gas. If we continue to heat a liquid, the particles begin to vibrate more and more before eventually turning into a gas. When a liquid boils and undergoes evaporation, the particles have enough energy to break apart from each other, to break the bonds that are forming up the liquid. This forms a gas. At this point, the particles are able to move freely, they are able to flow over each other and able to spread out. They have the highest amount of energy. So in summary, as we go from a solid to a liquid, or a liquid to a gas, we are increasing the amount of kinetic energy that each particle possesses. By doing so, we are breaking the forces of attraction between each particle and enabling them to spread out from each other. The key information to know is that solids have strong forces of attraction holding everything together in this regular lattice structure. As I mentioned, the particles don't move from their position, but they do vibrate around their position. Solids have a definite shape and volume, so they are unable to flow. As they get hotter, the particles vibrate more, causing the solid to expand slightly. In liquids, there are weak forces of attractions between the particles, but they're randomly arranged and, as we looked at, free to move over each other, but they tend to stick very, very close together. They have a definite volume, but not a definite shape, so they will spread out to fill a container. The particles are, however, constantly moving with random motion. The hotter the liquid gets, the faster these particles move, causing liquids, just like solids, to expand slightly when heated. Finally, in our gases, the forces of attractions are very, very weak. They're free to move and they do very far apart from each other. The particles in gases travel away in straight lines. Gases don't have a definite shape or volume and will always fill a container. they will always fill whatever you put them into. The particles are moving constantly with random motion, however, the hotter the gas gets, the faster these particles move. This means that just like solids and liquids, gases will also expand when heated, or their pressure will increase if they're not able to expand any further. At the top end of the grades, looking at the grade 9, it's important to also note that this particle model, whilst good, isn't perfect. In reality, the particles aren't solid or inelastic, and they're certainly not perfect spheres. They're going to be atoms, ions, or molecules. So knowing the model doesn't show all of the forces between the particles, so we can't show fully how strong it is. However, it is a good model. All state changes are physical changes. This means that they are easily reversed and that the chemical properties of the substance do not change. We can see that these are reversible reactions because if we were to heat ice to form liquid water, we could easily freeze that back to reform the ice. This is because the particles themselves aren't changing in any way. What is changing is the arrangement, their movement, and the amount of stored energy in each particle. There are also states that exist outside of this standard model. The one that is known most about is plasma, which is found at the very top end of the temperature scale. By doing so, the particles now have a huge amount of kinetic energy, and the protons and electrons are able to move apart from each other. We can also link state changes to energy graphs. Here we see a solid being heated before it melts into a liquid, before the liquid boils and evaporates into a gas. When looking at changes of state, we also need to consider pure and impure substances. A pure substance is a substance that only contains one type of atom or molecule. An impure substance is also known as a mixture. Pure substances have a defined melting and boiling point. For example, pure water melts at 0 degrees and boils at 100 degrees. Impure substances do not have a defined melting and boiling point. Instead, they melt or boil across a range of temperatures. On top of this, the melting point will be decreased, whereas the boiling point will be increased. We can also look at both the boiling and melting time. For any substance, when it starts melting, it will then continue to melt until all of the substance has melted. Only at that point will the temperature then increase further onto a potential boiling point. One way in which the exam boards could ask a question is as the following. The melting point of gallium is 29.8 degrees Celsius and its boiling point is 2204 degrees Celsius. Predict its state at 25, 100 and 2205 degrees Celsius, drawing diagrams to support your answer. If gallium melts at 29.8, that would mean that it is still a solid at 25. It doesn't boil until 2204, therefore would be a liquid at 100 degrees Celsius, and finally a gas at 2205. We could also look at using potentially a gallium teaspoon. Obviously, we would argue that this wouldn't be a successful idea, as the temperature of the water is above the 29.8 degrees required to melt gallium. Our big question for today was to describe the changes that occur when a solid changes into a liquid and then into a gas, referring to the arrangement, movement and energy of the particles. I want you to pause the video now and attempt this question. So, looking at the mark scheme, what we've got is that as temperature increases, those attractive forces between particles are overcome. As the solid is melting, the temperature would stay constant. The substance is still being heated, but the added energy is making the particles break away from their fixed arrangement until the whole of the solid has melted to form a liquid. The remaining attractive forces between the particles in a liquid are then overcome due to evaporation and boiling. Adding more energy causes the particles to move fast in all directions. For further information on the bonding of different compounds, please refer back to the bonding video available on this channel.